Whether it's your phone, laptop, or TV, you're watching this video on a miracle of technology. As much as it might seem like it, these devices aren't made from literal magic, but materials with unique and surprising properties. But as special as they are, it shouldn't surprise you to learn that they're also hard to find enough of. Today, we're consuming them faster than ever, and researchers are starting to worry that we may be running out. This idea that we may exhaust our supply of certain important elements is called criticality, and it's already starting to shape what the technology of the future might look like. We're going to look at a bunch of reasons why certain elements might become scarce, but the obvious one is that there just wasn't a lot to begin with. A great example of this is indium, which sits 2 rows below aluminum on the periodic table. Yet aluminum is more than 1,000,000 times more abundant in Earth's crust. As much as 75% of the world's indium production is used to make indium tin oxide, which has the remarkable property of conducting electricity while remaining completely transparent. It's a key component in LCDs and touchscreens, so you're probably looking at or through some indium right now. It's also used in solar panels and for the ball bearings in Formula 1 race cars. The world is planning on building a lot of solar panels and LCDs in the coming years, so we're going to need a big supply of indium, which is kind of a problem. In fact, some estimates suggest our demand for the element may begin to exceed production by 2030. Unfortunately, increasing that production is easier said than done. Indium is mined mainly as a byproduct of zinc extraction, but even then it's rare, with abundances anywhere from 1 to 100 parts per million in zinc ore. So a big increase in indium production means a glut of zinc, whether we need more of that metal or not. Instead of producing more indium, another option is to simply use less of it. Since we're not likely to give up on televisions and solar panels, that means finding an alternative. For screens, that could mean antimony, but the criticality of that element is even higher than that of indium, so not a great substitute. Manufacturers of solar panels could replace indium with graphene or carbon nanotubes, but these advanced materials are still experimental and very expensive. It's not only very scarce elements that face supply risk either. Some materials have high abundance, but low concentration. The poster children for this problem are the dubiously named rare earth elements, which consist mainly of the elements in the lanthanide series. Scientists initially discovered them as trace components of minerals that themselves were very rare. This gave rise to the notion that they were among the Earth's scarcest elements. Today, we know that that's not actually true. Cerium, for example, is as abundant as copper, and even the rarest of the rare earths is 200 times more common than gold. What makes them rare is that unlike many other metals, they didn't end up in concentrated deposits in the Earth's crust that are easy to find and mine. The rare earths have the highest criticality of any element, not just because they're extremely difficult to extract, but because they're also used in an incredible array of products. Cerium is the only element other than iron that produces sparks when struck. If you've ever used a flint to start a fire or a lighter instead of a match, you've probably used an alloy of the two called ferrocerium. Ferrocerium is valuable because it sparks at a uniquely low temperature, making things like lighters easier to use. The unusual properties of rare earths mean they pop up in all sorts of modern technology. Up to 50% of the glass in your smartphone camera, for instance, is made of lanthanum. Neodymium magnets are used in spinning hard drives and DVD players, while yttrium, europium, and terbium create the colors in your TV screen and LED lights. A big part of why technology today is so different from a century ago is that we've learned to effectively extract and use these exotic materials. Rarity isn't the only reason an element can have high criticality. A material can be relatively abundant, yet difficult to mine safely and ethically. As governments around the world become more concerned with the environmental and human impacts of mining, they may create regulations that further diminish the supply of a critical element. These broader limitations can mean that even if a particular substance is safe, it faces restrictions based on the byproducts of its extraction. A good example is monazite, a mineral rich in rare earth elements. After processing, monazite can contain up to 70% cerium and lanthanum, enabling the creation of all the products we just talked about. But monazite also contains thorium, uranium, and radium, which are highly regulated radioactive elements. The cost and difficulty of dealing with these toxic byproducts led to the closure of America's only rare earth element processing facility in the early 2000s. Another example is arsenic, which is a byproduct of copper and gold mining. In the form of gallium arsenide, it's a key component in the manufacturing of semiconductors, which are the foundation for basically all modern technology. Arsenic is also used in the process of pressure treating wood, like what you might build a deck or mailbox post out of. It's also poisonous and can cause cancer, which means it hasn't been mined in the United States since 1985. That's the tension in this class of criticality. Some of our most important technology relies on some pretty nasty stuff. Right now, there are people and places willing to do that dirty work, but there's no guarantee that this will always be true. The last big cause of criticality is what researchers call vulnerability to supply restriction. It's the idea that there are people and politics behind everything we do, and that those factors are inherently unpredictable. predictable. For many elements, it's not just that they're incredibly rare or dangerous to produce, but that the production happens in very few places, which, if you think about it, is a natural consequence of our two previous factors. If a resource is very rare, there are probably only a couple places in the world where it can easily be found, and as more countries regulate the mining industry, there are fewer and fewer places willing to do the extraction. If something happens to restrict production in those few places, whether it's deliberate or not, the global supply of a critical element could be threatened. The world first started to understand this about 50 years ago when what's today the Democratic Republic of the Congo underwent a period of severe civil unrest. Back then, the DRC was the world's chief supplier of cobalt, and the nation's unrest led to a sharp drop in exports. Today, the country still supplies about 2/3 of the world's cobalt. It's used in a bunch of things, but the most important by far is the construction of lithium-ion batteries. That's the battery technology that powers our phones and laptops, but it's also used in many modern electric cars. If electric cars are going to be a big tool in the fight against climate change, that means the effort will hinge in part on the stability of the DRC. And cobalt isn't the only example. Geology and chemistry don't care about national borders, but because of how mineral deposits are often concentrated, one nation can end up controlling the lion's share of a particular element. The US, for instance, produces 73% of the world's helium, which is critical for the use of MRI machines. China provides 95% of the gallium used in LED lights, as well as around 70% of arsenic, antimony, and all the rare earth elements. In fact, of the 35 most critical elements in the world, China is the leading producer of at least 20. This is where geopolitics, technology, and geology can overlap, sometimes uncomfortably. Whether it's China, the US, or somebody else controlling most of one element, that's a lot of influence concentrated in one place. That's why some researchers believe the key to overcoming this form of criticality is to focus on finding more ways to make the same stuff. Another way might seem even more obvious. We could just reuse the material we already have. Recycling important elements from discarded products would help resolve all three factors that produce criticality. Reusing material would slow the extraction of a finite resource and reduce the need for further mining, which could have a big environmental impact. One study found that recovering metals at a recycling plant produced 80% fewer emissions than mining an equivalent quantity, which is a win for stopping climate change. And unlike extraction, which can only happen where ore deposits are located, stuff can be recycled anywhere. That could reduce the market power of dominant producers. The challenge is that recycling individual elements is a lot harder than, say, recovering the plastic from a milk jug. These materials often exist in only trace amounts as part of a highly processed product like a circuit board. Worldwide, less than 1% of rare earth elements are recovered, and in 2018, no arsenic was recycled anywhere in the world. Instead, it ends up adding toxicity to your local landfill. Reversing this trend will require techniques as innovative as the materials themselves. One idea is phytomining, which uses specially selected plants to extract trace elements from recycled products. The plants concentrate the metal in their own structure, which can then be destroyed to retrieve the substance. Another option is bioleaching, which uses engineered bacteria to dissolve and extract metals like copper and cobalt. It's already used to produce more than 20% of the world's mined copper, and researchers are investigating how to effectively use bioleaching in recycling programs. Ultimately, we don't really have much of a choice when it comes to dealing with criticality. Our modern forms of transportation, power generation, and medicine have come to rely on these nearly magical materials. To keep their benefits, we need to learn to deal with their scarcity. But it's not all bad news. Criticality isn't a single static problem. It's a function of our ability to engineer and discover. As we find new ways to solve problems and more accessible, sustainable materials to use, we can sidestep some of these challenges. Others will require learning to live within the constraints of what's here on Earth, but that research is already underway. Still, the next time you buy a slick new phone, make sure you don't simply throw the old one away. The elements inside could literally be priceless. Thanks for watching this episode of SciShow, which was brought to you with the help of our patrons. Patrons earn cool perks, plus they help us make awesome videos for everyone to enjoy. If you'd like to join up, check out patreon.com/SciShow.